Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to continue our lecture on Chapter 8. In the previous video, we discussed the nomenclature and the physical properties of carboxylic acids. In this video, we're going to focus on the reactions of carboxylic acids. The first reaction that we're going to focus on is the synthesis of carboxylic acids. Carboxylic acids can be prepared through the oxidation of two types of starting materials, aldehydes and primary alcohols. Oxidation in this context refers to the process of increasing the number of bonds from carbon to oxygen, often by converting a hydroxyl group or a carbonyl group into a carboxyl group. Strong oxidizing agents are going to be required for this type of transformation. Some common oxidizing agents that are used to synthesize carboxylic acids include sodium dichromate, potassium dichromate, chromium trioxide, and potassium permanganate. Now let's walk through the example that's shown here for the synthesis of carboxylic acid. We start with a primary alcohol. This is a molecule where the hydroxyl group is attached to a carbon that is only bonded to one other carbon atom. In this case, the structure that's shown is ethanol, which has a two-carbon chain. When treated with potassium permanganate, this primary alcohol is fully oxidized to form a carboxylic acid. In this case, the resulting product is acetic acid, which is a two-carbon carboxylic acid. Importantly, it is only primary alcohols that can be oxidized all the way to carboxylic acids. Secondary alcohols typically stop at the ketone stage, and tertiary alcohols cannot be oxidized under these conditions because they don't have a hydrogen atom that's attached to the carbon bearing the hydroxyl group. In addition to alcohols, aldehydes, which already contain a carbonyl group, can be oxidized directly into carboxylic acids using the same strong oxidizing agents we just covered. Now let's move into another very important reaction pathway for carboxylic acids, and that is nucleophilic acyl substitution. Carboxylic acids and their derivatives, they commonly undergo nucleophilic acyl substitution reactions. And in these reactions, a nucleophile attacks the carbonyl carbon, and that leads to substitution of the leaving group. Let's go through the general mechanism step by step. First, the carbonyl carbon of the carboxylic acid is electrophilic, meaning it is partially positive due to the high electronegativity of the oxygen atom. This makes it an attractive target for a nucleophile, which is a species that donates a pair of electrons. So in the first step of the mechanism, the nucleophile attacks the carbonyl carbon, causing the electrons in the carbonyl bond to temporarily shift up to the oxygen atom. So we're temporarily breaking the double bond and forming a tetrahedral intermediate. In the second step, under acidic conditions, the hydroxyl group can be protonated to form a better leaving group, specifically water. This sets up the molecule for elimination. So the tetrahedral intermediate then collapses, reforming the carbonyl double bond and ejecting the leaving group, which in this case is a molecule of water, to complete the substitution. So the end result is that the original hydroxyl group is replaced by the incoming nucleophile, forming a new carbonyl-containing product. So to summarize, the two main steps of nucleophilic acyl substitution is 1, a nucleophilic attack on the carbonyl carbon forms a tetrahedral intermediate, and 2, elimination of the leaving group occurs along with the reformation of the carbonyl bond. Now, nucleophilic acyl substitution, this is a key pathway that enables carboxylic acids to form important derivatives, such as esters, amides, and anhydrides, which is what we're going to discuss next. Let's start with the formation of amides. Carboxylic acids can be converted into amides when the incoming nucleophile is either ammonia, which is NH3, or an amine, which is a molecule that contains a nitrogen atom bonded to one or more alkyl groups. Let's go ahead and work through the general process. We start with a carboxylic acid, and this contains a carbonyl group and a hydroxyl group attached to the same carbon. This carboxylic acid is going to react with ammonia or an amine. In this reaction, the nitrogen atom of the amine acts as a nucleophile, and it attacks the carbonyl carbon of the carboxylic acid. During the course of the reaction, a molecule of water is going to be eliminated, specifically the hydroxyl group from the carboxylic acid and a hydrogen atom from the amine combine to form water, which leaves the system. The result is the formation of an amide. This is a functional group characterized by a carbonyl group that is present and it's directly bonded to a nitrogen atom. Amides are named by replacing the oic acid suffix of the parent carboxylic acid name with the suffix amide. If there are any alkyl groups that are attached to the nitrogen atom, they're not considered part of the main carbon chain. Instead, each alkyl group that's attached to the nitrogen is named separately at the beginning of the molecule's name. And these groups are going to be introduced with the prefix N to indicate that they are attached to the nitrogen atom rather than the carbon chain. So for example, if we have an amide with a methyl group that is attached to the nitrogen, we would use the prefix N methyl at the start of the name to indicate that. Second, let's take a close look at the resonance properties of amides. Amides are stabilized by resonance between the lone pair of electrons on the nitrogen atom and the carbonyl group. The nitrogen can donate its lone pairs into the carbonyl system, and that creates a partial bond character between the nitrogen and the carbon. This delocalization of electrons is illustrated in these two drawings of the resonance structures. So in the first resonance form, we have the standard carbonyl structure with a single bond between the carbon and the nitrogen. In the second resonance form, the double bond character shifts between the carbon and nitrogen. So it forms right here, and the carbonyl oxygen now carries a negative formal charge, while the nitrogen carries a positive formal charge. Because of this resonance stabilization, the carbon-nitrogen bond in amides is shorter than a typical carbon-nitrogen single bond, and the carbonyl carbon becomes less electrophilic compared to a normal carbonyl group. This partial double bond character also gives amides their relative rigidity, and it makes them less reactive towards nucleophilic attack compared to other carboxylic acid derivatives such as esters. Lastly, let's discuss cyclic amides. Cyclic amides are also called lactams, and a lactam is simply an amide group that is incorporated into a ring structure. The naming of lactams uses Greek letters to indicate the size of the ring and the position of the nitrogen atom relative to the carbonyl group. For example, A beta-lactam is a four-membered ring where the nitrogen is attached to the beta carbon relative to the carbonyl group. A gamma-lactam is a five-membered ring where the nitrogen is attached to the gamma carbon relative to the carbonyl group. And finally, a delta-lactam is a six-membered ring where the nitrogen is attached to the delta carbon relative to the carbonyl group. Lactams are important structures that are found in biological molecules. For instance, beta-lactams form the core structure of penicillin antibiotics. Now that we've covered amides, let's move on to discussing esters. Esters can be thought of as a hybrid between a carboxylic acid and an ether. Structurally, they contain a carbonyl group, just like a carboxylic acid, but instead of a hydroxyl group attached to the carbonyl carbon, we have an alkoxy group, which is an oxygen atom that's bonded to an alkyl group. The formation of esters from carboxylic acids is called esterification. And this is an example of a condensation reaction, meaning that two molecules combine to form one larger molecule with the loss of a small molecule as a byproduct. In this case, the small molecule lost is water. Now let's walk through the mechanism carefully. We begin with a carboxylic acid and an alcohol. The first step is actually the protonation of the carbonyl oxygen of the carboxylic acid. Protonation increases the electrophilicity of the carbonyl carbon, making it more susceptible to nucleophilic attack. Next, the alcohol acts as a nucleophile and it attacks the carbonyl carbon. This pushes the electrons from the double bond up onto the oxygen atom, temporarily forming a tetrahedral intermediate. Within the tetrahedral intermediate, one of the hydroxyl groups can become protonated, and that's going to convert it into a good leaving group, specifically water. Following this protonation, the intermediate collapses. The bond reforms between the carbon and the oxygen of the carbonyl, and that ejects the water molecule. The final step is deprotonation of the remaining oxygen atom to neutralize the positive charge, and that results in the formation of the ester. So the overall transformation replaces the hydroxyl group of the carboxylic acid with an alkoxy group that's derived from the alcohol. The reaction produces an ester as the main product and water as the side product. Now let's take a moment to talk about the naming of esters. When naming esters, we first name the alkyl group that was originally attached to the alcohol. This group is named first as a separate word, and then we name the carboxylic acid part by replacing the oic acid ending of the parent acid with OH. So for our example mechanism here, the alkyl group that was originally attached to the alcohol was an ethyl group, and then the carboxylic acid part was ethanoic acid, which we changed to ethanoate. So the full name of the product is ethyl ethanoate. Finally, we move on to the cyclic forms of esters. Esters that are cyclic are called lactones. And these are formed when a hydroxyl group within the same molecule reacts with a carboxylic acid group, forming a ring structure with an ester linkage. Just like cyclic amides were called lactams, cyclic esters are called lactones, and they're named according to the size of the ring and the position of the ester linkage using Greek letters. So for example, alpha acetolactone is a three-membered cyclic ester. Beta propiolactone is a four-membered cyclic ester. And then gamma butyrolactone is a five-membered cyclic ester. The Greek letter designation corresponds to the position of the oxygen relative to the carbonyl group in the ring. Now, the next carboxylic acid derivative that we want to cover is anhydrides. Anhydrides are molecules formed by the condensation of two carboxylic acid molecules. Condensation, again, refers to a reaction where two molecules are joined together with the loss of a small molecule. In this case, again, water. Let's walk through how an anhydride forms. We start with two molecules of carboxylic acid. In the reaction, one carboxyl group loses a hydroxyl group, meaning an oxygen and a hydrogen, while the other carboxyl group loses just a hydrogen atom. These two components combine to form a molecule of water, which is eliminated from the system. The two remaining fragments, each containing a carbonyl group, become connected by a single oxygen atom between them. This forms the structure of the anhydride, two carbonyl groups bonded to the same oxygen atom. For example, if we start with two molecules of acetic acid, we can form acetic anhydride along with water as a byproduct. Now, anhydride formation, it typically occurs under heat, and because it's a condensation reaction, it's favored by removing water from the reaction mixture to drive the equilibrium forward. So in summary, anhydrides are formed by the condensation of two carboxylic acids with the loss of water, creating a molecule with two carbonyl groups linked through an oxygen atom. Now that we've covered the carboxylic acid derivatives, let's move on to another important reaction of carboxylic acids, reduction. Carboxylic acids, they can be reduced to primary alcohols by using a strong reducing agent. One commonly used reagent for this purpose is lithium aluminum hydride. Let's walk through the reduction mechanism step by step. We start with the carboxylic acid, where the carbonyl carbon is highly electrophilic. The first step involves attack by a hydride ion. This is a hydrogen atom carrying an extra electron, and it's provided by the lithium aluminum hydride reagent. The hydride attacks the carbonyl carbon, and that pushes electrons up onto the oxygen atom, and it breaks the double bond temporarily. This produces a tetrahedral intermediate in which the carbon now carries both a hydroxyl group and a newly added hydrogen atom. Next, the intermediate collapses by elimination of the leaving group, which is typically a hydroxide ion, and that results in the formation of an aldehyde. However, under the reaction conditions, the aldehyde doesn't remain as the final product. Lithium aluminum hydride is a very strong reducing agent, and it immediately delivers another hydride to the aldehyde carbonyl carbon, repeating the same nucleophilic attack and formation of a second tetrahedral intermediate. After protonation during workup, the final product is a primary alcohol. Therefore, through this two-step reduction, first to an aldehyde, then to a primary alcohol, the carboxylic acid is fully reduced. Now, it's important to note that milder reducing agents such as sodium borohydride, these are not strong enough to reduce carboxylic acids. Only a powerful reducing agent like lithium aluminum hydride is effective. From here, let's move into the final two major reactions that we need to cover for carboxylic acids: decarboxylation and saponification. First, let's talk about decarboxylation. This describes the complete loss of the carboxyl group from a molecule, and it's released as carbon dioxide gas. Let's go through the mechanism that's shown here. In the structure drawn, we see a molecule with a carboxyl group positioned beta to a carbonyl group, meaning that the carboxyl group is located 2 carbons away from a carbonyl. This arrangement is important because it allows the molecule to undergo a 6-membered cyclic transition state during the reaction. In the mechanism, the electrons from the carbon-carbon double bond adjacent to the carboxyl group shift towards the carbonyl group, and that facilitates the release of carbon dioxide. Simultaneously, a hydrogen atom is transferred to stabilize the remaining structure. So the immediate product is an enol, which is a molecule containing both a carbon-carbon double bond and a hydroxyl group attached to the same carbon atom. However, enols are typically unstable relative to their keto forms. Therefore, a rapid tautomerization occurs, meaning the enol quickly rearranges itself, resulting in the formation of a keto form where the double bond moves between the carbon and oxygen, therefore restoring the carbonyl group. So in summary, during decarboxylation, a carboxyl group is lost as carbon dioxide. An enol intermediate forms temporarily, and it tautomerizes to the more stable keto form. Now let's move to the final topic, which is saponification. This is a reaction in which long-chain carboxylic acids, commonly known as fatty acids, react with strong bases such as sodium hydroxide or potassium hydroxide. When a fatty acid reacts with a strong base, a salt is formed. This salt is what we recognize as soap. Here the process is simple. The hydroxide ion from the base deprotonates the carboxylic acid, forming a carboxylate anion. This anion is then paired with a metal cation, such as sodium or potassium, forming a fatty acid salt. The structure of a typical soap molecule has two distinct regions. It has a non-polar hydrocarbon tail, which is long and hydrophobic, meaning it doesn't interact favorably with water. The second region is a polar carboxylate head group, which is negatively charged and hydrophilic, meaning it interacts well with water. Because of this dual nature, soap molecules contain both hydrophilic and hydrophobic regions. When soap molecules are placed into aqueous solution, they spontaneously organize into spherical structures called micelles. In a micelle, the polar heads face outward, interacting with the surrounding water, while the nonpolar tails are buried in the center of the micelle away from the water. This structure is what allows soap to dissolve grease and oils. The nonpolar tails can interact with nonpolar substances like oils, trapping them inside the micelle, while the polar heads keep the micelle soluble in water, allowing it to be washed away. So in summary, for these last two reactions, decarboxylation results in the loss of carbon dioxide and formation of a new carbonyl compound, often through an enol intermediate. And saponification is the base-promoted conversion of fatty acids into soaps, which arrange into micelles in aqueous environments, with polar heads on the exterior and nonpolar tails on the interior. And with that, we've completed this chapter. I hope this has been helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.